So today we're going to work on 2.4, day 6, very similar to what we did yesterday, but instead of polynomial inequalities, we're going to be working with rational inequalities. So if you want to go ahead and pause the video and work on this problem to start right here, give it a shot, see if you can figure out how to do some rational inequalities. There are very many similarities between the rational inequalities and the polynomial inequalities. Otherwise, I'm going to go ahead and walk through this problem, how I would go about it if I had never learned about rational inequalities, but I had the prior knowledge of polynomial inequalities. So just like we had on polynomial inequalities, we needed 0 by itself. And then they gave us a little hint here to say, what are the key numbers? So our polynomial inequalities yesterday, a lot of times we had a quadratic or we had something that could be factored. So we would factor those numbers and solve for the left side. Well, similarly, there's nothing really here we can factor, but we do notice that it's kind of like two factors in the numerator and denominator. We haven't learned anything about this yet, but we're going to in a minute. So I'm just going to go ahead and guess that I can find my two key numbers by using these two factors. So I have x plus 2 and I have x minus 5 equals 0. And then after I solve that, I have my key numbers being -2 and 5. So if these are my key numbers, I'm going to go ahead and just kind of continue the pattern of what we did yesterday. So I'll make my little table, and again, from least to greatest, I can say that one interval would be from -infinity to -2, because that's the smallest. Now again, very, very important, be careful. We know it's greater than or equal to, so this would be a bracket for the -2. And then -2 to 5, with again both of them being brackets, and then 5 to infinity. I don't need this last section. There we go. All right, so now again, just following the pattern that we had yesterday for the polynomial inequalities, once we have our key numbers and we've broken down the sections on the number line, I can find some test points. So just like we did yesterday, a number in the interval from -infinity to -2 might be -3. And if I test -3, what we do with this number is we put it back into what used to be the factored portion. But what's nice about this rational inequality is that essentially it's already kind of factored. So if I plug in a -3, I have -3 plus 2 over -3 minus 5. Now again, as we talked about yesterday, we know that we're looking for that left side's output to be greater than or equal to 0. So the numbers themselves don't necessarily matter as much as whether just the number is positive or negative. So in the numerator, I have a negative number, because -3 minus 2, or -3 plus 2 is -1, over a -8. So a negative divided by a negative is always going to be a positive. It doesn't matter whether it's positive 1/5 or positive 24, it's just going to be a positive number. So we have a positive number for that first section, and since that's what we're looking for, we know this is one part of our solution set. Second number that we're going to plug in is 0. So if I plug in a 0, 0 plus 2 over 0 minus 5 is going to be a positive over a negative, which would give me a negative output, which is not what I'm looking for. And then the last section, if I plug in 6, 6 plus 2 over 6 minus 5 would be a positive over a positive, which again gives me another positive. So the final solution set would be from -infinity to -2. Again, be very careful that you are including brackets because it is or equal to. If you do not include brackets, you do not have the full solution. You will be missing part of those solutions, and that's never good. Again, also, as a reminder from yesterday, please make sure that you are using the key numbers in your intervals, not the test numbers. So do not use the negative infinity to negative 3 or the 6 to infinity. You want to make sure you're using your key numbers. So very, very similar concept to what we did yesterday with the polynomial inequalities. We're just going to be using rational inequalities, so we have a little bit of division in here. Note here, it says rational inequality key numbers. It's kind of just what we talked about. So through that example, just by testing it out, we noticed that the key numbers are where the numerator and the denominator are equal to 0. If you find those x values that make the numerator and denominator equal to 0, those are our key numbers that will split your number line into the solution sections. And again, just like we talked yesterday, I could have picked -5, I could have picked -20. All of those numbers are going to have the same output as any other number in that section, which is why we want to find those key numbers to break up our number line. So same process as the polynomial, plug in the test points and identify true or false. So the first most important thing is always get 0 by itself first, because if you don't have 0 by itself first, then you cannot determine a section to be true or false based on positive or negative, because it's not being compared to 0. So the first thing we want to do here is get 0 by itself. Then we want to find the key numbers by solving for the numerator and denominator. So this one does not factor, but we can solve it. So x squared minus 7 equals 0. X equals plus or minus root 7. So those are two key numbers there. The next part is x squared plus 16 equals 0. X squared equals negative 16. So x equals plus or minus 4i. Now, because we're dealing with the number line and the graphs, we do not include imaginary numbers. No imaginary numbers, because, again, if you picture it, remember yesterday when we graphed our left side of the equation and you found the x-intercepts, imaginary numbers are not on your graph. Therefore, you cannot use them as a basis for the inequality, because they do not exist in the dimension of an xy axis. Okay, so in this case, we only have two key numbers, which makes it a little bit easier here. If I go ahead and make my intervals, we know from least to greatest, negative infinity to negative root 7. This time, again, we are not including it, so we need a parentheses. Negative root 7 to root 7, and then square root of 7 to infinity. Again, all parentheses. Now, we should know our perfect squares, which will help me pick a number in that interval. So negative root 9, right, is less than, so it's in that interval. Negative root 9 is 3, so I'm going to pick negative 3. It's in that interval. If you're unsure, you can go even one more and go to negative root 16, which would be negative 4. But I know negative 3 is in that interval. So again, I have to take this number and I have to plug it in somewhere, either in a factored version or the original. In this case, I don't have a factored version, so I got to kind of put it in there. But using your number sense, I know that a negative number squared has to be positive. Or you could just plug it in all the way if you want, but you can use your number sense and your knowledge of all these PEMDAS and whatnot to figure out positive or negative. But essentially, I have 9 minus 7 is going to be a positive 2 over 9 plus 16 is a 25. That is a positive number, which means it is not in my interval because I'm looking for negative outputs. Second one, a number between negative root 7 and root 7. 0 is always a nice one. So I have 0 squared minus 7 over 0 squared plus 16. I have a negative number. That is in my interval. And then again, 3 I could use on the other side. So I have 3 squared minus 7 over 3 squared plus 16. That's going to be a positive 2 over a positive 25. That's again a positive, which we do not want. So our solution set here would be negative root 7, square root of 7, and all those numbers, not including those on the edge. Now again, just like we did yesterday, you have to read the instructions, but some may allow a calculator. you could plug in the entire rational expression on the left side, and what you'll get, if you zoom properly and you have the correct window, is you would get something like this. And if you already guess it, we know from yesterday that the key numbers are these x-intercepts. So this would be negative square root of 7, or whatever the decimal is, square root of 7, whatever the decimal is. And then you know, because we're looking for the negative, right, where it's less than 0, we know that this is our solution set. So if you're allowed to use a calculator, and we talked yesterday, make sure that you follow the correct instructions, because there will be questions where you are asked to use the calculator or not, and you got to be able to do both. So just be aware of that. But you can use that strategy if it says you are allowed to use a calculator. You can also use the table feature on the calculator. So if you just plug the graph in, you hit second table, you can also just find the outputs of those inputs. Okay. Next question, if we move down, just like we did yesterday for our polynomial inequalities, and like we did above, we want to find those key numbers first. So if we look on the left side, we notice we can actually factor the numerator and the denominator. By factoring the numerator and the denominator, it's going to make it a lot easier to find these key numbers. So we have x equals -1, +1, -5, and -3. And again, be very careful that you have 0 by itself first, and then when you solve, you don't make any mistakes as you're finding those key numbers. So just like we did with our polynomial inequalities and above, we're going to go ahead and create our interval chart. So we have -infinity to -5. We have -5 to -3. And we are doing all brackets because we know that it is or equal to, besides the infinities, so that we know that the solutions we just found, those key numbers, are solutions to our inequality, because we just found those key numbers. And again, when we break this down, we already have our table. You got to find some test numbers, but we know that we can graph and just look above and below to determine which section is true or false, because it's being compared to 0. If you want to just, if you're allowed to use the calculator based on the instructions, you can graph the whole rational expression on the left side at this point and just look either at the table for the test numbers or at the graph itself and determine positive or negative. However, we do need to be prepared, and we need to be able to solve this without a calculator. So I'm going to go ahead and do that for this problem because of that. So if I plug in a -6, like we talked yesterday, I don't want to plug it into this entire mess. I don't want to square it -1 and then square it on the denominator +8 times -6. We're going to end up with a messy number, or a big number, big fraction. So just like we did yesterday, I would highly recommend that if it is factored, you just plug in your test numbers to that factored expression. It's going to make it a lot easier to work with, because again, it's being compared to 0, so all we care about is the positive or negative. So when I plug in that -6 for all of my x values, we have a negative number, -5, we have a -7, we have a -1, and we have a -3. Just by plugging them into that factored form, I have positive or negative outputs. And the nice thing about polynomial inequalities, when they can factor, and rational inequalities, when they are factored, if they are factored, everything's being multiplied or divided. And again, because we're comparing it to 0, all we care about is positive or negative. So in this case, we have a positive over a positive. So your whole output would be a positive, which is what we're looking for. So the -infinity to -5 is part of our solution set. If we move to the next section, a number between -5 and -3 could be -4. And again, if I plug it into the factored form, I have a negative times a negative over a positive times a negative. Again, following your rules, you know that you have a positive over a negative gives you a negative, which is not in our solution set. Next part, we have a -2. Plug those in. We have a positive times a negative over a positive times a positive. I'm sorry, we have a negative times a negative. That's right, -2 times plus 1 times -3. So in this case, you would have a positive, which is part of your solution set. And that's something to note. It does happen in some cases where you may have two negatives back to back or two positives back to back for your outputs. But if it does happen, just double check real quick because it doesn't happen often. So if it does happen, just give a quick check, double check your math, double check your algebra, and make sure that it does work. So in this case, we did catch that mistake. We fixed it. In the next section, if we use 0, we have a positive times a negative over a positive times a positive. That's a negative. And then the last section, plug in 2. We have a positive times a positive times a positive and positive. So we have another positive. So we have 3 solution sections and our whole interval for the solution set using brackets for all of them again, because they are all included, would be that. Okay. On the next page, if we take a look at number 3, we're going to notice for numbers 3 and 4 that 0 is not already by itself. So again, it's something that sometimes you take a little bit for granted, because it does happen often where you're already given a problem with 0 by itself. But it is important to make sure you deal with that before you move on. So we got to get 0 by itself. And if you recall from Algebra 2, we do that by moving it over. So 2x over x minus 2 minus 3 is less than 0. And then again, this is a very, very, very important note. We need to get a single fraction. Okay, you cannot find your key numbers unless you have a single rational expression by itself. So in order to do that, we've got to find an LCD. We do that by multiplying numerator and denominator by x minus 2. We have done this before. Just be very careful with the negatives. It's very easy to miscalculate or make a basic mistake here. So be very careful about that. And then once you have that single rational expression on the left side, now we're at a spot where we can go ahead and finish the problem. And at this point, we're just following all the steps that we did on the first page. So our key numbers, if we solve them, we know negative x plus 6 equals 0. So x equals 6 and x equals 2. So our key numbers are 6 and 2. So negative infinity to 2, not including it. And then 2 to 6. And then 6 to infinity. Plug in 0, 3, 7. And again, because when we changed from the first part up here to down here, you can either plug the 0 into the original, but then you need to look from the left side and see how it compares to 3. So at that point, you're not allowed to just go based on positive, negative. So what I would always recommend is, again, always use either the factored part that's compared to 0 if possible, or again, like in this case, it's just a rational expression being compared to 0. So you always want to look at it compared to 0, because then it makes it a little bit easier and you're just comparing it as positive or negative. So if I plug in 0, I have a positive 6 divided by a negative 2, which is a negative. since we're looking for less than 0, this would be part of my solution set. This would be a positive over a positive, which is a positive not in our solution, and then a negative over a positive, which would be a negative. So our solution set is negative infinity to 2, and then from 6 to infinity. Okay. For the next one, if you're feeling really confident right now, I would say for this one, you probably can pause it, try the problem, and then unpause it and check the work. It's similar to the last one. It's the same concepts, just bigger numbers. But go ahead and try it. Otherwise, if you're still kind of working through them or have some questions, keep watching and we'll work through it together. So just like the last one, we need 0 by itself. So we got to move that over. And then once it is moved over and we have 0 by itself, we need to get that common denominator. We have two different binomials and then a constant. So in this case, we're going to have to multiply by the missing parts for each denominator. There are no overlapping parts, so we need to multiply both the numerator and the denominator by what is needed to get that common denominator. Okay, and then I'm just going to put arrows there. So they're going in the numerator and denominator. One thing to note here is because it's a least common denominator, once we've multiplied by all the missing parts, the denominators are already factored. So if you remember later, we're going to want to plug in our test points. It's a lot easier when the left side is factored. So I'm not going to distribute out the denominator because I do not want to be plugging into a complex part on the left side. That's already pretty simple there. It's factored. Now in the numerator, you could leave it up there, but we still need to find the key numbers. So in order to find those key numbers, we need to expand and combine like terms for that whole numerator. So we got to go ahead and distribute everything that's going on up there. We're going to have to FOIL up there, so we'll hold on to that one for a second. So we have 10x squared minus 10, minus 50x. And then we have plus 5x plus 25 times x minus 1. We're going to have to FOIL that out in a minute. And then minus x squared minus 25. That's a difference of squares, so that helps a little bit. So if we FOIL this one out, we have 5x squared minus 5x plus 25x minus 25. Go ahead and combine these like terms. We'll write this so it looks a little bit nicer above. So in this top, we're looking at all of, let's go purple, all of this. That's our whole numerator. So we go ahead and look for our like terms. We have 15, we have 14x squared. We have minus 30x. And we have, that's it, right? 25's cancel. So that's what we got. 14x squared minus 30x. So it ended up working out pretty nicely. And then again, in the denominator, we want to leave that factored. And then if we look back at the numerator, we can actually factor this a little bit more. We have 2x as our GCF. We have 7x minus 15. So what's really nice about this is our key numbers are pretty easy to find here. So we have our key numbers being 0. Do not forget that it is part of our factor. 2x equals 0, so 0. 15 over 7, which is just over 2. and then 5 and negative 5. So when we make our table, and again, based on your directions, if you're allowed a calculator, you can plug this part in right here. At this point, you can plug in this. It's less than 0. You can plug in this part to the calculator and see how it compares to 0. But we're going to do this by hand. Negative 5 to 0. And then 0 to 15 over 7, because that is roughly 2 point something. And then 15 over 7 to 5. And then 5 to infinity. And then, again, either by using the calculator if you're allowed, or your test points when you plug them into the factored form. If I plugged in a negative 6, I would have a negative times a negative over 5 times a, like I said, we should put that 5 in there, it's a positive, times a negative times a negative. So we have a positive output. And then if we plugged it in here, we have a negative 1. If you plug that in there, we have a negative times a negative times a negative, and then a positive. So that would be a negative number. And then if you go through this, you could plug in 1, which would be a positive times a negative, and then divided by a negative and a positive. So that would be a positive, and these are two of our, wait, this wrong? I'm sorry, we're looking for negatives here. So we have that section, these don't work. And then we have 3. So if we plug that in, we have a positive. We have a positive, we have a negative, and then a positive. So it would be another negative, that works. And then if I plugged in 6, they would all be positive. So that would be a positive, which does not work. So our solution set here is negative 5, 0, and 15 over 7 to 5. Okay. And then the final one here, again, at this point, if you're confident, you can try something, but we're going to notice this one's a little bit different zeros by itself, so that's nice. But when we go to find our key numbers here, we notice that this is not factorable. So I mentioned it yesterday, but we didn't go through any problems in our notes yesterday where there was a quadratic that was unfactorable, but we do know that when we're finding the key numbers, those are the x values that are solved for the numerator and or denominator. So even though we can't factor it, we can solve this one using, that's right, the quadratic formula. We all know it. We all love it. So go ahead and use that quadratic formula. We have negative 5 plus or minus 5 squared minus 4 times a times c all over 2 times a. So we end up with negative 5 plus or minus the square root of 25 plus 4 is 29 all over 2. Now again, if you're allowed a calculator, you could plug that in and you could just look. And you have to use the exact value right here that we're going to use for your intervals. So when we make our table, we'll go ahead and write that. But please do not use a decimal unless it says to round. So we have our interval is from negative infinity to negative 5 minus root 29 over 2. And that is included. And then negative 5 minus root 29 over 2 to negative 5 plus root 29 over 2. And then negative 5 plus root 29 over 2 to infinity. So this is our interval set. We do know, if you're not allowed to have a calculator, that root 29 is roughly 5 point something, because the square root of 25 is 5, and then square root of 36 is 6. So that would be negative 5 plus 5 point something over 2. So since it's not 6, but it's over, we know this has to be a fraction, right? This has to be a positive decimal, right? Positive decimal. And then between, this is less than 1, by the way. Because again, it's positive decimal. So then the denominator, we have negative 5 minus 5 point something over 2, right? So if it's roughly negative 10 point something divided by 2, we can guesstimate it's going to be negative 5 point something, right? Now again, if you have a calculator, you can guesstimate these, or you can plug them in and use the exact values, or you can use a graph. But if you don't have a calculator, such as the SAT, or you get something like this, this is very helpful number sense and work with numbers to be able to figure this out. So while we normally get as close as we can to our key numbers, because these are pretty strong estimates or guesses here, I might pick a number that's a little bit further away. So on the left side here, we're using the negative 5 point something. I might pick negative 7. So if I pick negative 7 or negative 10 or something else easier to work with, it might be a little bit easier to plug in. So 5 over negative 7 squared plus 5 times negative 7 minus 1. Sorry for the small writing here. I'm running out of room on my paper. But I know that that's a positive over what's 49 minus 35 minus 1. I know this has to be also a positive. So this section would be positive. And the nice thing about this one, in the middle section, I can just plug in 0, because 0 has to be between the negative 5 point something and the fraction greater than 1. So if I plug in 0, I end up with 5 over negative 1, which has to be a negative. And then, and this is, I'm sorry, this is the section we're looking at because we're looking for negatives. And then the last section, again, we said it should be a fraction less than 1, but just to be safe, I can pick 2. And if I pick 2, we have 5 over 2 squared plus 5 times 2 minus 1, which is going to be, I'm plugging in 2, it's not 5 squared. It's 5 over 4 plus 10 minus 1, so it's going to be a positive again, which again, we're not looking for. So the only solution set that works is 5 minus root 29 over 2 and negative 5 plus the square root of 29 over 2. Again, with brackets because it is included.